Hey guys, Professor Doney here as promised, putting some online videos together to give you some at-home work and some additional resources to support what we're going through in class. Not sure how many videos I'll put together here today, but I'm going to work through Chapter 2 a little bit so we can stay sort of a little ahead schedule and have more time in class for questions if you have any. So we're going to start off here in Chapter 2. We've been talking about waves. And we've talked about two different types of waves. We've had EM waves, and we've had mechanical or physical. And EM is talking about light. They are strictly transverse waves. And we're talking about mechanical, and mechanical for us are physical waves, and physical waves require a medium. Hope my handwriting is working out here for you. I know it's not the best in class and sometimes even worse here. So EM waves, they don't need a medium. However, mechanical physical ones do because they physically interact. And that is what sound waves are, which is what we're using. We're using in the ultrasound range. And again, in the ultrasound range, it's greater than 20,000 in general. But for us, it is specifically in the 2 to 10 megahertz or 2 to 12, depending on which textbook you are going from. So let's look at two different types of waves there. Transverse, beyond that, we can talk about transverse waves. And transverse is if we have a wave that is traveling from left to right along this line, the displacement of the wave is going to be transverse or across. That means across this way, if this is the direction or velocity of the wave. If we're talking about longitudinal, which are a little harder to draw, longitudinal is going to have areas of high compression stretching out, high compression again, stretching out, high compression again. These are longitudinal waves, meaning along, the displacement is along, sort of particles move back and forth this way. Now this again is for sound. This is what really is happening. We have increased pressure here called compression. We have decreased pressure here called rarefaction. Increased pressure again, decrease, increase. And that's how a pressure wave is. And a lot of times they'll draw a wave for this type with having sort of this shape. So here comes the wave. And what these purple lines are supposed to represent is the peak of the wave, the high pressure point. So a lot of times they'll show that drawn that way. Transverse is ocean waves and the fan waves for a sports team. Although, again, sound waves are longitudinal, we are going to draw them this way so that we can do some labeling and describing of some information. So let's draw quickly a transverse wave here. And that could go on, and I'll sort of just try to complete it here and see if I can finish it out. Not too bad. All right, so what do we have here? We have drawn a transverse wave. However, we would say this is a sound wave. Why? Because we can label the amplitude. That's A up, and that's A down. We probably would call that a positive A and a negative A, but it always goes above and below the baseline or the average. Think of this as a flat ocean. There's no waves at all. It's like a glassy lake. If it goes above, there has to be a below part. So the amplitude is going up. So A here is amplitude. Wow, that's really ugly. What's going on? And in our world, we are going to use volts. All right. Voltage is what vibrates or sends a signal into the transducer and vibrates it and causes sound waves to come out. All right, I'm going to finish up quickly because I'm hitting the time limit. What else can we label on here? We can label this as a peak, and that is a trough. And the idea is when a wave starts, it must finish a complete cycle or complete wave. So that would be one cycle or one wave or one length of the wave.